Hello champions, welcome back to the Brahmastra 2.0 series, and in today's video we are going to discuss all the important questions from the chapter coordination compounds. Okay, so I have taken question from model question paper of last year, this year, question bank of last year, this year. So this is mix of all important questions, so do not miss any question from this video. So before starting, let's understand the mark distribution, or I can say the weightage of this chapter. So the weightage of this chapter is actually 11 marks, where 2 marks will be 1 marker question and 3 you will get 3 marker question. So 3 3s are 9, 10, 11. Okay. Now let us start with the first question, which is your MCQ, and these all MCQ are your HOTS question. Okay. So what type of bond is there in between ligand and metal in a complex compound? So type of bond here is actually coordinate covalent bond. Okay. Next, if the secondary valency in COCl3.4 NH3 is 6, the solution conductivity in silver nitrate corresponds to dash electrolyte. Now, if you see here, if the secondary valency is 6, right, that means what? There will be total, you have to have COCl3 and NH3 whole 3, and you need to have one NH3 outside. Okay. Now, the solution, okay, 1 second. The solution conductivity in silver nitrate corresponds to, okay, so if you see here, you have to have 1 chlorine outside because you are treating it with silver nitrate, and here you will have 2 chlorines. Okay, so now if you see what will be the charge of this complex, the cobalt will be in +3 state. Okay, this is in -2 state, so this is total 1 + 1 and this is -1. So it is a 1:1 electrolyte. So option number A is the correct answer. Next, given that 1 mole of NiCl2.6H2O with excess of AgNO3 precipitates 2 moles of AgCl, what is the secondary valency of nickel? Now see, if you are precipitating 2 moles of AgCl, that means 2 chlorine will be outside the complex. So what will be the formula here? NiH2O whole 6, okay, and then dot Cl2. Now here you can see that 2 moles of AgCl will be formed. So the secondary valency is 6. So option number D is the correct answer. Next, what is the sum of the oxidation number of cobalt in the given compounds? Okay, so sum of the oxidation number of cobalt. So you have X here, then H2O is 0, Cn is -1, En is also 0, and then you have +2. So X is equal to +3 here. Okay, next we have this one. Cobalt is X, bromine is -2, plus 0 is equal to +1, and you have X is equal to +3. So total we have 6 charge, the addition will be +6, option number D here. Next, what is the primary valency of iron in the coordination entity of the compound? The primary valency of the iron in the coordination entity of the compound. Okay, primary valency means they are asking you the oxidation state of Fe here. Now, if you see, this compound must have, see, it is Fe +3 and FeCN6 4-, right? So this is the charge of the complex. Now, if you see here, this is X -6 -4, and you will get X is equal to +2 here, right? So that is why option number B is the correct answer. Next, which of the following compounds has enantiomers? So you know, any compound which will have I can say non-superimposable mirror image will have the enantiomer. Here you can see this compound will show enantiomerism, so that is why option number B here. Now if you see the structure of aluminium, C2O4 is a didentate ligand, so I will draw like this. Right, now if you draw the mirror image of this one, it will be in this form. So it will be in this form, right? So that is the mirror image enantiomer of this one and non-superimposable. So option number B will be the correct answer. Next, linkage isomerism is seen in compounds having dash ligand. Linkage isomerism is where you have, I can say, ambidentate ligands, right? Which have more, you have ambidentate ligands. Like for example, suppose this is metal, okay? You have a ligand NO2. So here N can bind, that is also possible, and with M, O can also bind. right? So in both of these cases we will get linkage isomerism, so we need to have an ambidentate ligand for that, so that is option number D here. Next, the compounds are given which type of isomers. So here you can see that when you dissolve this one, okay, you will get this compound and this SO4 ion, and when you dissolve this one you will have this complex and chlorine ion, right? So different types of ions will be produced, so that is why you will have here coordination isomerism, that is option number B. Next, we have which of the following orbitals does not belong to T2G orbital. So dx, dy, dz belongs to T2G, and Eg part dz square is a part of Eg. Okay, so option number D here. Next, what will be the electronic configuration of D5 in terms of T2G and Eg in an octahedral field when delta O is less than P? If delta O is less means it is a weak field ligand. Okay, you will have splitting like this. And we want D5 configuration. So 1, 2, 3, 4 and 5. So that is T2G3 Eg2, which is option number C here. Okay. Next, we'll see the first 3-marker question here. So what is the postulates of Werner's theory? This is very important question. Every year this question is repeated. So Werner says that this complex will have two types of valency, primary valency and secondary valency, right? Primary valency is what? Primary valency are normally ionizable and are satisfied by negative ions. Means primary valency you can think of as the charge of the complex, okay? And what is secondary valency? Secondary valency are non-ionizable, and these are also neutralized by neutral and negative ions, and it is almost not, it is equal to the coordination number of the metal. Okay, so secondary valency is the coordination number of the metal. Clear? Now second question, on the basis of the following observation made with aqueous solutions, assign the secondary valency to metals in the following compounds. Okay, so this is your exercise in text question, so I have taken from there. So you see in the first one, we are getting 2 moles of AgCl is produced, right? So that means what? 2 chlorine will be outside. So I have PD NH3 whole 4, okay, and 2 chlorine will be outside. Next we have again 2 chlorine outside. So I have nickel and H2O whole 6 and 2 chlorine outside. Okay, next here I have PtCl4 2HCl. So here that is 0, it is there, that means here all the groups will be present inside. So we have PtCl4 HCl. Okay, sorry, HCl is there, HCl can be outside but that will not precipitate. Next you have 1 chlorine will be outside. So we have CO NH3 whole 4, okay, and we have Cl2 and 1 chlorine outside. Okay, now we have here 0, so everything will be inside. Here the compound will be like this, PT NH3 whole 2 and Cl2. Okay, understood this one? Now there is no chlorine outside, so there will be no precipitation. Now coming to the next question, what are chelating ligands? So this is a definition based question. So the ligands which can bind from more than, the ligands which have more than one donor site, okay, and can bind to the metal from more than one bond and form a cyclic structure with the metal is called as a chelating ligand. Okay, so you can see when a di or a polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal atom, it is said to be a chelate ligand. Such complexes called chelating complexes tends to be more stable than the similar complexes containing unidentate ligand. So whenever there is a chelation, whenever there is a cyclic ring formation takes place, it always increases the stability of the complex. Next question is nomenclature. So here the names are given, you just need to draw the structure for that. Okay, so first one, let's see here. The first one, question number 1 is what? Tetrahydroxidozincate. Okay, tetrahydroxidozincate. So I have Zn here, okay, OH tetrahydroxidozincate, this is there. Okay, now how can I find the charge of this complex? Zincate is there, that means you have to have a negative charge here. Zn is +2 and oxygen is -4, so I will get -2 here. Okay, next let's do question number 2 here. Hexaamine cobalt sulfate. Okay, so you have here hexaamine, okay, cobalt sulfate. Okay, now here we have okay, so +3 is there, Okay, you can see this is plus 3, 0, so this will be plus 3 and this is minus 2. Now there can be a cross multiplication and you will get CONH3 whole 6, 2 and SO4 whole 3. Okay, so that is there, plus 3 and SO4 whole 2. Next, third one, what we have? Third one is potassium tetrachloridopalladate 2. Okay, potassium is there. Okay, next we have tetrachloridopalladate, PdCl4. Okay, now here you see we have the charge of palladium is plus 2 and chlorine is minus 4. 2 minus 4 is minus 2. So minus 2 will come here, that then will cross multiply here, and 1 will come here, we will get this compound. Next we have question number 4 here, that is potassium trioxalatochromate. Okay, so I have potassium, then you have chromate trioxalato. Okay, then you have 3 and 6 plus 3, right? So it will be 3 here. Next we have fifth one, diamine dichlorido platinum 2. Okay, diamine dichlorido platinum 2, right? So we have here platinum is there. Okay, dichlorido is there, diamine is there. Okay, diamine dichlorido platinum 2. So here it is 2 minus 2, so 0. So that means the net charge of the compound will be 0 here. Okay, so these are the structures that you can do. Next we will do IUPAC naming. We'll write the name of the compound. So here you can see the first one here, I'll write hexaamine. Okay, just a minute, 1 second. Yeah, so we have hexaamine. Okay, then cobalt. Okay, then you have here, what is the charge of cobalt here? This is plus 3, right? So cobalt will be 3 here, and then we have chloride. Okay, hexaamine cobalt 3 chloride. That is the first option we have. Next, coming to the second one here, we have this particular compound. So we will have tetraamine. Okay, then we have chlorido, tetraamine chlorido, then I have nitrito N here, nitrito N, then we have cobalt. Okay, now if you see this one, X minus 3 minus 2, so NO2 is so I can write the charge of cobalt, let it be X. Okay, I mean this is a neutral ligand, so 0. Chlorine is minus 1, NO2 is minus 1. Okay, and if you see, this is the charge of the compound. Okay, I have chlorine also minus 1, that is equal to 0. So cobalt is equal to plus 3. Okay, so we have here cobalt 3 and then we have chloride. Okay, next third one we have nickel, ammonia and chlorine. So it will be hexaamine. Okay, hexaamine nickel. Okay, hexaamine nickel. Then you can see here that you have nickel charges 2, then you have chloride. Okay, so that is how we can complete these questions. Now moving to the sixth one, again you have some IUPAC name, you have to write more questions. So I want all of you to practice these 3 questions, and I have already explained how to do this one. Try these questions and put down your answers in the comment section. I will pin the answer in the comment section, or I'll reply you in the comment section, but I want all of you to practice these 3 and put down your answers in the comment section. Okay. Next question, we will go for isomerism. Draw the cis and trans isomer for this one. Now if you have ML4X2, okay, when you have ML4X2, the cis isomer will be, the trans one will be like this. You have here L, L, L and L. Okay, so this is trans. Next we have cis here, that is M, X, X, L, L, you have L and L. Okay, this is cis. Next you have B, which is your MLL2X2, MLL2X2. okay, now here if I see M is there, okay, you have X, and you have L, right? I'll draw like this. 1 second. Yeah, I can have L like this, and you have L and L like this. Okay, so now this one is what? This is my transform. Okay, this is the transform. Now how will be the cis form? The cis form will be M. You have like this, so I can have L here, and I can have L here, and you can have X and X. X are on the same side, so this is your cis isomer. Okay, now coming to the next one, MAL3X3. so this will not give you cis and trans, this will give you facial and meridonial. Okay, you will get facial and meridonial. So you have M, so I'll draw all this like this. So if I have all the L on one side and all the X on one side, so this is facial. Okay, and then if you have M like this, where we have all the L on one plane and X on the opposite, then it is called as meridonial. Okay, so these are the isomers that you need to draw. Next question is, why is geometrical isomerism not possible in tetrahedral complexes? So we know that in tetrahedral all the bonds are equal, right? So there is no difference in that. So tetrahedral complexes do not show geometrical isomerism because the relative position, okay, of the ligands attached to the central atom are the same with respect to each other. Clear? Next is, what do you mean by optical isomerism? So see, optical isomerism is a phenomenon where a compound is able to rotate the plane polarized light. Okay, if a compound is able to rotate the plane polarized light, then we call that compound as optically active. Clear? Now what is this optical isomerism? So those compounds which are optically active shows optical isomerism. Now how will you know by seeing a compound whether it is optically active or not? So for that, the optical isomers, okay, are the mirror images that are non-superimposable on one another, and they are called as enantiomers. Okay, now these enantiomers have all the properties same except that one property, that is the rotation of plane polarized light. If one enantiomer is rotating it in clockwise direction, the other will rotate it in anti-clockwise direction. Okay, that is the difference here. Next we draw the optical isomers of the given compound. So let us draw here. So we have the first one, optical isomers. Always remember the cis form will be optically active, not the trans form. So I will draw for the first one. You have PT, okay, then we have like this, that is En, I have En, and we have Cl. Okay, now if I draw the mirror image here, PT will be there, and then I have like this, okay, Cl, and then we have N like this, and we have N and N like this, right? So these are non-superimposable mirror images of each other, so that is why they are optically active. Now coming to the second one, we have a COEN whole 3. Okay, so we have like this, we have like this, this is one group is present, this is one group is present, and this one is present. Okay, now we will have the mirror image of this one, that is CO. Okay, and we have this one will be like this. Okay, this is like this. Okay, sorry, the mirror image will slightly be different, not like this. Okay, see, it is like this one, and this one. So this one will be superimposing on this one, so that is why this will be optically active, and they are non-superimposable also. Okay, so they are the mirror images and non-superimposable on each other. Next, out of the following entities, which one is optically active? So cis form is active, trans form is not active, so it is option number A here. Okay. Next question number 11, how many geometrical isomers are possible in the following coordination entities? Now if you see this first one, okay, so you will have the exact compound like this, you will have a didentate ligand and its mirror image, right? So this one will have 2 isomers, and if you see this one, it will have facial and meridional, so this one will also have 2 isomers, okay. Next, explain linkage isomerism with an example. So in linkage isomerism, as I told you, we need to have an ambidentate ligand, okay. So how do we show linkage isomerism? We need to have an ambidentate ligand. Now suppose this is a compound here, its linkage isomerism will be like this, where you have NH3 ONO and Cl2. Okay, so ONO will bind. Now see here, nitrogen was binding to the metal and here oxygen will bind. So that is the difference, and that is how we will get the linkage isomerism. Next question is about ionization isomerism. So we know that when a complex is dissolved in the solvent, it produces ions, right? So if you have different ions, if you have if in a complex you can have different ions produced, then they will be called as ionization isomerism. Now here what happens, this forms of isomerism arises when the counter ion, means which is present outside the complex, in a complex salt is itself a potential ligand, means that counter ion can behave as a ligand, okay. So what it does, it displaces the ligand, which can then become the counter ion, means there is an exchange between the counter ion and the ligand which is present. The counter ion is a potential ligand and it replaces the existing ligand, and the existing ligand becomes the counter ion. Now I'll show you an example. If you see SO4 and Br, right, so these all are these both are counter potential ligands, so Br can come here and SO4 can go out, so that will give you ionization isomerism. Next, solvation isomerism. Solvate isomerism differs by whether or not a solvent molecule is directly bonded to the metal atom or merely present as free solvent molecules in the crystal. So it is very similar to ionization isomerism, but you have to use here water molecule. Now if you see here H2O6 and Cl3, okay, now what I can do is I can bring one water molecule outside and one chlorine I can take inside, so that will affect the color of the compound, and these two are called as hydrate isomerism or solvate isomerism. Next, what is coordination isomerism with an example? When you have 2 coordination pairs and the ligands of both the coordination pairs can be exchanged between them, then we call it as coordination isomerism, okay. So this type of isomerism arises from the interchange of ligands between the cationic and the anionic entities of different metal ions present in a complex, okay. So here what will happen, NH3 can come to Cn and Cn can come to NH3, so that can be exchanged between these two, okay. Next, we have explain the hybridization, magnetic property and the geometry of CONH3 6 3+. So like this, similar questions will be asked and it is given in your book. You will be getting questions similar to this for COF6 3-, then you will get for NiCl4 2- and NiCN4 2-, okay. So I'll be telling you the way how to write the answer, and the same thing you have to follow for all the compounds. So let us see first here. First, what I have to write, step 1. Step 1 is to write the cobalt electronic configuration, okay, which is argon, next 3d7 and 4s2. Next, we have what is the oxidation state of cobalt here, it is +3, okay, so that will give me argon and 3d6, okay. Now here you can see, I'll draw 1 2 3 4 5, right, 1 2 3 4 5 and 6. Now what you have after 3d, we have here 4s also, okay, and we have 4p also, okay. Now what happens here, we know that NH3 is a strong field ligand, right? So what it will do, it will do pairing of electrons. So NH3, okay, is a strong field ligand and it can pair electrons, okay. So what will happen then, you have 3d6, so all the electrons will paired up here, so we have 6, so 1 2 3 4 5 and 6, okay. 3d6 is there, then we have 4s, then we have 4p, okay. 4s is there and we have 4p, okay. Now you know the coordination number is 6, right? So there will be hybridization. So these 6 orbitals D2sp3, okay, D2 sp3 will undergo hybridization, and now 6 new hybrid orbitals are created. Okay, this is very important. How many orbitals have mixed? 6 orbitals have mixed, and 6 or new orbitals will be created. So we will have, okay, now these are the 6 new hybrid d2sp3 orbital. Okay, now in each of them what will happen? Who will donate electrons? The ligand, that is NH3, will come and donate the electrons. Okay, so I'll just write down here. Okay, so these all will donate the electrons. Clear? Now with this the answer writing part is over. Now let's answer the question. What is the hybridization? Hybridization is D2sp3. Next, magnetic property. If you see magnetic property, you have to see the electrons of the metal. Okay, now you see in this metal there is no unpaired electron. If it is no unpaired electron, then it will be diamagnetic. Okay, next we have the geometry here. Okay, now geometry will be what? Geometry will be octahedral, because for coordination number 6 the geometry is always octahedral. Okay, now what we have to see here, which is important, is how to the thing, I'll tell you all the hybridizations and the shapes so that you can remember. Okay, now see, for coordination number 4 there are 2 types of hybridization. One is sp3, another is dsp2. Now sp3 hybridization will give you tetrahedral geometry, and dsp2 will give you square planar. Okay, now similarly we have for coordination number 6, and here we have d2sp3 hybridization and we have sp3d2 hybridization. Okay, and both of these geometry are called as octahedrals. Clear? Done? This is clear? Okay, let's move to next question. Limitations of VVT. So you have to remember certain limitations, like it involves a large number of assumptions. What are those assumptions? And it does not give you any quantitative interpretation about the magnetic data. Okay, how do we get paramagnetic, diamagnetic? Through valence bond theory we cannot explain that. Next, does not explain the color of the compounds. Then it also does not tell about the stability of the complex, and it does not distinguish between weak and strong field ligands. So any 3 points you can write down here. Next, what is crystal field theory, and explain this one. So what happens, let me tell you the story of crystal field theory. So we have the metal, right? Metal have their d electrons. Now when the ligand comes near the metal to form bond with the metal, so ligand will come with their electrons to donate to the metal. Now metal have their d electrons, so there is inter-electronic repulsions. The electrons of the metal and the electrons of the ligand, there is repulsion between them. Now due to this repulsion, what happens? The d orbital split into 2 halves. One comes d2g level and the other one is eg level. So this splitting, or the gap between the 2 d orbitals, is called as your crystal field splitting energy. Now how do we write this one? The crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from electrostatic interactions between the metal and the ligand. So according to CFT, the bond is purely ionic. Next, ligands are treated as point charges in case of anions, or point dipoles in case of neutral molecules. Okay, so these are point charges. Next, the 5d orbital in an isolated gas, metal, atom or ion have the same energy, that is they are degenerate. So when they are in the metal, they all have the same energy, but when the ligand approaches, there is repulsion, as a result of which the d orbitals split here. Okay, so this degeneracy is maintained if a spherically symmetrical field of negative charges surround the metal atom. However, when this negative field is due to ligands, okay, the negative end of the dipolar molecules like NH3 or water in a complex, it becomes asymmetrical, with the degeneracy of the d orbitals is lifted, and it results in the splitting of the d orbital. Okay, now we'll show that in the example. D orbital splitting of octahedral complex. Every year, many years these questions have been asked, so you have to remember, you have to do proper leveling. Okay, so first these are the degenerate d orbitals, means where all the orbitals have the same energy. Now when the ligand approaches in the spherical form, so the energy increases of the d orbital, but still they are degenerate. Now when the ligands approaches, there is repulsion, because of which the d orbital split, and this value is called as your crystal field splitting energy, the difference between the T2G level and the EG level. Okay. Next, we'll talk about the tetrahedral crystal field splitting. So here also we have first all the 5 d orbitals have the same energy. Now in the spherical field their energy increases, okay, and after that it splits into 2 parts. Here we have TE and here we have T2. Okay, now here we have dz square and dx square minus y square, and here we have dxy, yz and zzx. Clear? Okay, next we'll see question number 21. So this question is very important. CrNH3 is paramagnetic while NiCN4 is diamagnetic. Okay, now see, I'll explain both the structure here. Let's draw for how we have drawn the hybridization. Let us understand in that way. Let me explain you, but you don't have to write in that way. I'll tell you how to write so that you will get the full marks. Now let us see the structure of chromium. Okay, it is plus 3. Chromium plus 3 is D3. Okay, now here we have 1, 2 and 3. Here we have D3 electrons. Okay, now what will happen? This is D, this is 4s and this is 4p. Okay, 4s and I have 4p. Now the hybridization, coordination number is 6 here. So what will happen? We need 6 empty orbitals. So you see that already 6 empty orbitals are available here. Means you don't have to do any pairing. Though NH3 is a strong field ligand, okay, here pairing should take place. But here the requirement of pairing is not there. Why? Because without pairing only 6 orbitals are free. The main objective of doing pairing is to create vacant orbitals, right? But since you have already 6 empty orbitals are available which can undergo hybridization, there is no need of doing pairing here, and that is why here you can find 3 unpaired electrons are there, and that is why this is paramagnetic. Now let's talk about nickel. CN4 2-, so nickel will be plus 2 state here. Its electronic configuration is 3d8. Now if I draw 3d8, okay, 1 second, yeah, 1, 2, 3, 4 and 5, 1, 2, 3, 4, 5, 6, 7 and 8. Now here what will happen? Cn after 3d we have 4s, okay, I have 4s and after that I have 4p. Okay, now you can see that here, okay, since Cn is a strong field ligand, the pairing of electron takes place. Okay, pairing of electron takes place and you will get this dsp2 hybridization. Okay, so I needed this empty orbital for the hybridization, so we need to do pairing, and here you see there is no unpaired electron, so that is why this is diamagnetic. Okay, so let us see now how to write the answer. See, you have to write that CrNH3 3+ has D2sp3 hybridization and 3 unpaired electrons, so it is diamagnetic. Sorry, so it is paramagnetic. This is small typing error, so it is paramagnetic. Okay, next, similarly NiCN4 2- has dsp2 hybridization. Now dsp2 hybridization, and as I just showed you, there is no unpaired electron there, so that is why it is diamagnetic, because of no unpaired electron. Okay, next we will see NiCl4 2- is paramagnetic while NiCO4 is diamagnetic, but both are tetrahedral. Both are tetrahedral means both are having sp3 hybridization. So let us again understand this one by doing the valence bond theory. Now NiCl4 2- nickel is +2 oxidation state, right? It has D8 configuration. How will I do D8 configuration? You can see here, yeah, so I have 1, 2, 3, 4, 5, 6, 7 and 8. Okay, now here 3d8 is there, and then we have 4s and then we have 4p. Okay, now here you can see that we need 4 empty orbitals, so there will be sp3 hybrid orbitals. Okay, there are 4 empty orbitals and they will undergo mixing and we will get sp3 hybridization. Now here you can see that we have 2 unpaired electrons, so that is why it is paramagnetic. Okay, this is very simple and clear. And why we are not doing here pairing? Because it is a weak field ligand. In case of strong field ligand, there will be pairing. In case of weak field ligand, there will be no pairing. So that is why here we are getting 2 unpaired electrons, so it is paramagnetic. Now let us see NiCO4. Okay, in NiCO4, if you see, the nickel charge is 0. Okay, so and nickel configuration is what? Nickel configuration is 3d8 and 4s2. Okay, so we have here 3d8. Okay, 1 2 3 4 5 6 7 8, and then we have 4s2. Okay, now these 2 electrons will pair up here. Okay, these 2 electrons will pair up here, and you will get this empty orbital. Why here pairing takes place? Because CO is a strong field ligand. So these 2 electrons will pair up here. Okay, and we will get an empty orbital here. Okay, then we have 4p here, and we will have sp3 hybridization will take place. Clear? This is done. So now with this, what will happen? This part 4sp3 hybridization is there, and that will lead to your since there is no unpaired electron here, there is complete pairing of electrons, so that is why it is diamagnetic, and this is paramagnetic. Okay, so understood. Now how to write this answer? You have to simply write down. See, you have to simply write down NiCl4 has sp3 hybridization. Okay, and it has 2 unpaired electrons, so that is why it is paramagnetic. NiCO4 has sp3 hybridization but no unpaired electrons, so it is diamagnetic. Okay, next is FeH2O6 is strongly paramagnetic, whereas FeCN6 3- is weakly paramagnetic. Explain. Now strongly paramagnetic means you have more number of unpaired electrons, and weakly paramagnetic means we have less number of unpaired electrons. Now let us see how many Fe3+. If you see, okay, Fe3+ is D5 configuration. Now in the first one, you have here, you have 1 2 3 4 and 5. This is 3d, then we have 4s, okay, and then we have 4p. Okay, now here you see this is d5 configuration. Okay, 1 2 3 4 and 5. We have d5 configuration, 5 electrons are present. Now this is, since H2O is a weak field ligand, there is no pairing of electrons. Okay, now these 5 electrons are there, and these 5 electrons can actually create the paramagnetism, and the magnetic moment will be equal to root over of 5 plus 2. Okay, this is the formula. Now let us go for FeCN6 3-. Now see, FeCN, so what will be the hybridization here? It will have sp3d2 hybridization. Now FeCN6 3-, if you see here also Fe is in d5 configuration, but Cn is what? It is a strong field ligand. That means pairing of electron will take place here. So all the 6 here, 5 electrons will paired up, and they will, you will have 3d in this form. Okay, 1 2 3 4 and 5, and this d2 is available, 3d is then we have 4s, and then we have 4p. Okay, so you have now d2 sp3 available for the hybridization. So now here you can see that you have only 1 unpaired electron, and here we have 5 unpaired electrons, so that is why this is more paramagnetic and this is weakly paramagnetic. Okay, so how can I write that? So you can see here FeH2O6 has 5 unpaired electrons, whereas FeCN6 has only 1 unpaired electron. So that is why this is strongly paramagnetic, and this is weakly paramagnetic. Next, the solution of nickel is green, but a solution of NiCN4 is colorless. Why? So see, now the color of the transition elements is due to d-d transition. So we have understood that when the ligands are coming, okay, when ligands approaches the d orbital split, okay, when the ligand approaches the d orbital split, and these unpaired electrons can undergo d-d transition, because of which we can see the color of a compound. Now what happens? So what is the basic criteria for having colored? We need to have unpaired electrons. Now if you see in nickel, okay, Ni2+ with water. So nickel configuration is what? Ni2 plus configuration is 3D8. Okay. If I have this 3D8, we will have, okay, 1, 2, 3, 4, 5, 6, 7 and 8. I will have 2 unpaired electrons, and the hybridization here will be sp3d2. Okay. Now because of these 2 unpaired electrons can undergo transition, there is a color obtained. Now if you see NiCN4 2 minus, okay, NiCN4 2 minus, okay, so here nickel is in +2 state, okay, and it is 3D8. Okay. Now 3D8, if you see, it will be like this. Okay. Yes. Now 3D is there, then we have 4s and we have 4p. Okay. Now this one will be DsP2 hybridization. Okay. Now this is my DsP2 hybridization, and this can actually like this DsP2 hybridization, you can see that there is no unpaired electron. If there is no unpaired electron, there is no DD transition. If no DD transition, then no color will be observed here. Okay. I hope this is clear. So now let's see how can we write this answer. We have to write very to the point answer. Now H2O is a weak field ligand, okay, so that is why there is unpaired electrons which undergo DD transition and the compound appears green. In NiCN4 actually, I'll just correct it, one second. Yeah. Okay, so in NiCN4 2 minus, we have absence of an unpaired electron is there, and that is why because here Cn is a strong field ligand, okay, and that is why there is no DD transition and no color of the compound. Let's see the next question here. Explain the violet color of the complex on the basis of crystal field theory. Now here you have to understand a very important theory, that is complementary color. So we have 7 colors, right? V, B, G, Y, O, R. So the color which the sample absorbs and its complementary color it emits. Okay, so if the sample is absorbing blue-green, so if the sample is absorbing blue-green color, then it will be visible to us as violet color. Okay, so you can see here that coordination compounds can exhibit colors attributed. So the reason is the crystal field splitting, and in that we have this DD transition. Now in case of titanium, what happens? It absorbs this blue-green color. Okay, it absorbs blue-green color, and that is why it is visible to us as violet color. Okay. Next, anhydrous copper sulfate is white, but CuSO4.5H2 is blue in color. Explain. This is very simple. Now see, we need to have in this anhydrous copper sulfate, okay, there is no ligand. If there is no ligand, all the d orbitals will have same energy. There is no DD splitting, and if there is no DD splitting, there will be no DD transition or no color formation. But in case of when we have this 5 water molecules, they actually approach the metal, and there is DD splitting, and these electrons present in the copper in this particular compound can undergo DD transition, and that is why it is appearing to us as blue. Okay, so you can see, due to the heating of water molecules evaporate and there is no ligand left, hence there is no splitting of d orbitals and no DD transition. That's why anhydrous copper sulfate is colorless. Okay. Next, what will be the correct order of wavelength of absorption in the visible region for the following? The correct order of wavelength of absorption. Now here you should know that E is equal to, E is equal to Hc by lambda, means E is inversely proportional to lambda. Okay, if the energy is more, then wavelength will be less. Now in this compounds, if you see where the splitting will be least, so if I just number them 1, 2 and 3, okay, now the third one, okay, water is a weak field ligand, NO2 is a weak field ligand, and NiNH3 is also a weak field ligand. Now what is the, NH3 is a strong field ligand. So what is the order of the ligands? You have first H2O, okay, the ligand strength, then we have NH3, and then we have NO3 minus. This is the strength of the ligands. Okay, that means what will be the splitting, how the d orbital will split. So in case of H2O, the splitting will be like this. In case of NH3, the splitting will be more than that, and in case of NO2 the splitting will be much more than that, right? So that means here the splitting is very high, sorry, NO3 minus, yes. So here the splitting will be very high, energy is very high, that means lambda will be the least one. So that is why this one will come first, okay? You have to arrange in the okay, increasing order we are telling, okay? Then we'll talk about NH3, its splitting is after this, so the energy will be higher here, so wavelength will be lesser. And lastly, in H2O, which is a weakest ligand, here the splitting will be less, energy will be less, and wavelength will be maximum, okay? Next question, discuss the bonding in metal carbonyls. Now see, carbonyls are a very special structure. Now in all the cases, in all the coordination compounds, metal and ligand bond is formed where ligand donates electron to the metal, and that too they all form coordinate bond, means ligand will donate electron to metal. But in case of carbonyls there is something special. What is special, ma'am? In case of carbonyl, what happens? The ligand donates electron to the metal, at the same time metal donates electron to the ligand, okay? So there is a double bond formed between metal and ligand. There is sigma bond as well as there is pi bond. So that we have to explain in this question. Now see, so what are the orbitals involved here? So I'll just explain like this. See, this is suppose metal orbital and this is ligand orbital. So ligand will donate its electron from, here what is the ligand? Here the ligand is Cu, okay? So metal ligand will donate from p orbital to empty d orbital, okay, from p orbital to empty d orbital. Now as I said, there is back bonding also, so there is donation from metal to ligand also. So metal will donate from filled d orbital, okay, from filled d orbital to empty pi star orbital. Okay, so this is what we have in the bonding structure. So this is the sigma bond and this is the pi bond, okay? So let us now, I'll erase this and we'll see the diagram and we'll also write the text here. So the metal carbon bond in metal carbonyls has both sigma and pi character actually, okay, not S and P, sigma and pi character. The sigma bond is formed by the donation of lone pairs of electron on the carbonyl carbon into the vacant d orbital. So this one, carbonyl carbon to the vacant d orbital. The MC pi bond is formed by the donation of a pair of electrons from a filled d orbital, okay, from the filled d orbital into the vacant antibonding pi orbital, okay, filled d orbital to vacant antibonding pi orbital of the carbon monoxide. Clear? Okay, now let's see the next question. I am not telling it in the form of question because this can be asked anywhere in MCQs or in any fill in the blank. So here are some important uses of complex compounds that you should know, and the most important is this one, that where in biomolecules where these complex compounds are found, coordination compounds. So first one is chlorophyll, which is having magnesium, hemoglobin is having iron, vitamin B12, which is called as cyanocobalamin, contains cobalt. So this can be asked in MCQ, so please remember this one, very important. Next we have Wilkinson catalyst, which is your PPH3 rhodium chloride, okay. Then in photography we have sulfite, okay, silver sulfite. And the next important is cisplatin, okay, it is used for the treatment of cancers or tumors in human beings, okay. So and there is EDTA, which is also used for the purification or for curing the lead poisoning. So these are different applications and you can go through it in detail because from here questions can be asked. So what are the important topics in this particular chapter? We have Werner's theory, then nomenclature, isomerism, VVT, CFT, definitely question will be asked, magnetic moment, colors, and the applications part. Okay, so students, this was all about this chapter and I hope this video was helpful for all of you. So thank you so much and I hope that all of you have got benefited from this lecture. If you have any doubt, put down in the comment section. I'll definitely address to you. Thank you so much and all the best. Your exams are coming, so let's put all our efforts, put all our hard work in the next few days. Let us not waste even a single day. Let us study every day because we have a very good goal, very big goal to achieve, right? With this note, thank you so much and stay tuned for the upcoming sessions and do not forget to subscribe the channel.